let's take a look now at the idea of working with surface integrals. We've been dealing with line integrals, so let's move on to the idea of integrating these surfaces in a vector field. I want to start off with the idea of the relationship between surface integrals and surface area. It's very similar to the relationship that we saw between line integrals and arc length. When we worked with line integrals, if f of x, y, z happened to be equal to 1, then the line integral was actually the same as the arc length of the arc that or the curve that we're working with. Now, perhaps the most common interpretation of a line integral through a vector field is the amount of work that was done by the vector field in the direction a particle moves along a path through that vector field. Now, likewise, jump into surface integrals. We want to define a surface integral such a way that if f of x, y, z equals 1, the surface integral results in the area of the surface. Perhaps the most common interpretation of surface integral, the most common use for it, of a surface integral of a vector field over a surface, is that of the idea of flux. And we think of flux as the amount, or perhaps the density of fluid, obviously if we're working with fluid dynamics, passing through the surface that resides inside this vector field. And instead of electromagnetism, the density of field lines passing through the surface. Now this is, cross that out, sorry, that's a bit of a typo there. Now, let's go ahead and start talking about the idea of parameterizing our surface. So if we have a surface that's parameterized by the vector function r of uv equals x of uvi plus y of uvj plus z of uvk. So I'm parameterizing the x, y, and z component from values in the uv domain. Now, in order to relate the domain of uv to the surface, we're going to first assume the parameter domain D is rectangular. So we're going to start off with the idea of a rectangular parameter domain u and v. And in reality, we'll see that it doesn't really matter if it's rectangular or not, but it certainly helps initially to start talking about this concept. So within u and v, I'm going to have some rectangular domain D. And I'm going to break this up into these little subrectangles like I've done many times before. So any subrectangle, say this one, is going to have dimensions delta u by delta v. And I'm going to make reference to this as Rij, region Rj in the parameter domain. So the area of Rij is then equal to delta u times delta v. So I want to connect this with my surface. So if I have a surface sitting over here in 3 space someplace, now the surface I'm going to break up into smaller patches, and I'm going to label these patches Sij. Now, within each patch, I'm going to pick some arbitrary point and call that point Pij star. Where here I'm just using the star to indicate that it's some arbitrary point inside of this particular patch. So the integral, the double integral over the surface area, over the surface of function of f of x, y, and z ds is going to then be equal to the limit, as m and n both go to infinity, of the double sum I equals 1 to n and j equals 1 to m of f of this point Pij star delta Sij. Now, we've done this sort of thing before, so this idea is actually not new. It's really kind of a review. Now, to evaluate the integral, what we want to do is approximate the area of each patch, each Sij patch, by a parallelogram in the tangent line. So this delta Sij is going to be approximately equal to the cross product of r, the partial of r with respect to u, cross the partial of r with respect to v, where obviously r is the parameterized surface. Oops, that's supposed to look like a cross product. There we go. Times a delta u delta v. Now this is going to connect my parameter domain to my surface in 3 space, where RU and RV are actually going to be, for some point UV, it's going to bring me to a corner of this patch where these two vectors are actually the tangent vectors at that corner. And as you may recall, one of the interpretations of cross products was that of the area of the parallelogram that's created by any two vectors when you put the tails together. So if I had one vector that went like this and another vector that perhaps looks like this, you end up with a parallelogram that looks kind of like this. And we could use a cross product to find the area of this parallelogram. So here this parallelogram is actually could be sitting in the tangent plane created by these two vectors. And just as a real quick reminder, the partial of u is going to be the vector partial of the x component with respect to u, partial of the y component with respect to u, partial of the z component with respect to u, and then obviously the partial with respect to v is going to be the partial of the x component with respect to v, partial of the y component with respect to v, partial of the z component respect to v, where again this r is my parameterized surface that I defined up here. Now if I should probably write this. If the components are continuous and the partials r of u and v are non-zero and not parallel in the interior of D, the parameter domain, then it can be shown that even if D is not a rectangle, even if it's not a rectangle, we can still show the double integral over the surface of f of x, y, z ds is equal to the double integral over the parameter domain of f of r of uv times the magnitude of the partial of u cross the partial of v dA, where dA is the area in terms of the parameter domain. Now what this does, this allows us to find a surface integral by converting it to a double integral over the parameter domain. Now notice here, if f of x, y, z happens to be equal to 1, then what that gives us is the double integral of the surface of 1 ds, which is equal to the double integral over the domain of the magnitude of the cross product of the r partials of r with respect to u and v dA, which is the definition of the area of that surface. This is how we found the area of the surface. Now also note, when evaluating this, don't forget that f of r of u of v that this quantity is actually found by direct substitution. So you're going to take whatever x is this whatever function of u and v it is, y is whatever function of u and v it is, and of course z is whatever function of u and v it is. Just go substitute these parameterized forms of these variables into f to begin with. So all of these will simply go into f of x, y, z.